Hey guys, this is part 5 of our discussion on time series forecasting. Well, in fact, probably part 6 because in the last tutorial we took a break to understand what LSTMs are. And before that, we actually used ARIMA, which is the traditional way of doing time series forecasting. And then we looked at neural networks, traditional feed-forward based neural networks for time series forecasting. And in this video, let's see how we can apply LSTM, for our time series forecasting. Well, spoiler alert, if you actually watch the one about neural networks, this is going to be almost identical, except instead of dense layers, we are going to just use LSTMs, okay? Or I should say in addition to dense layers. But let's actually also use a couple of variations of LSTM. Let's also do bidirectional and conv LSTM just to see how the result looks like. With the dataset I'm going to use, which is the airline dataset, there may not be much of a difference between any of these techniques, but please apply this onto your own data and see how these apply. My job here, or at least my focus here, is to educate you on all the ways and give you the code so you can go ahead and play with it, okay? So for that, let's jump into our Python IDE, which is Spyder that we use. And just a reminder, maybe in case you forgot, we are working with our air passengers dataset that I got out of Kaggle, and it has passenger data from January 1949 to December 1960. So total of 12 years and 12 months each. We have monthly data, so 144 observations. Not a lot. In fact, if you deal with stocks on an hourly basis for like an year, you'll have tremendous amount of data. Then LSTMs, go ahead and use it. This would be amazing exercise to do. Okay, so what am I going to do here? First of all, let's import the standard libraries. Okay, so hopefully you all know NumPy, Matplotlib for plotting, pandas, and math, because we'll do some basic math. And then let's go ahead and run those. And yeah, I can lump all of these together. So here we are using the sequential method to define our architecture for deep learning. And dense layer, let's go ahead and import, in fact, LSTM and flatten. These are all different layers we are importing from Keras. I like to work with Keras and not with the TensorFlow directly. Keras is based on TensorFlow because it's easier to program using Keras than TensorFlow. I am not a big fan of PyTorch because it requires you to typically work with classes and objects, and I'm not comfortable. I don't think most people are comfortable with that, but I appreciate if you work with PyTorch. Anyway, so these are the layers we are importing. We are also importing min-max scaler from scikit-learn, which is also a amazing library for traditional machine learning. Min-max scaler is it's basically it's taking the minimum value in your data, maximum value, and scaling everything to fit between 0 and 1. That's pretty much it, okay? And why do we do that? Because neural networks usually use different types of activation functions, and some functions do not work very well with numbers that are large, and so we want to bring all the numbers between 0 and 1 so we don't mess things up. Okay, and we want to look at mean squared error, so I'm going to import that out of scikit-learn, and I plan on actually including conv LSTM 2D, so we can just quickly have a look at how that works on this data. So these are all the other libraries that we are going to import. Let's go ahead and import them. And they should work no matter what version of Keras you have. I tested this on both my Python 3.7 and 3.5 and newer TensorFlow and older TensorFlow with Keras. So it should be fine. The only thing is I'm working on an older version here because I have an older GPU and I want to just use GPU for other purposes. That's the only reason. Okay, so now let's go ahead and read the data frame. It's and only use column number 1. This data frame has originally 2 columns. One is the date and the second one, well, the month and date. The second column is actual value. I'm just importing this second because this is what we are modeling here, okay? So here are the number of passengers in thousands for all these data points, and it should go all the way to 143 because we start at 0. Okay, now let's go ahead and plot it. We have done this many times in the past, and you can see how the trend is moving upwards, which means the total number of passengers are increasing every year. and there is a seasonality going on right here. But with LSTM, let's not worry about seasonality or anything, because we can model this as part of our LSTM. It takes care of that, or it's not dependent on that, just like traditional models. Okay. So now let's define our data set as dataset dot values, extract only the values, and convert these into float 32. When I do this dot values, it's converting my data frame or a pandas data frame into a NumPy array. That's exactly what I'm trying to do there, and convert that into a floating point 32. Why? Because I'm going to now do some math onto it, and I don't want to lose anything due to rounding errors. So what math am I going to do? Well, I'm going to apply this min-max scaler that we imported and scale everything to values between 0 and 1. So let's run that line just to show you. Right now my data set has values of 112, 118, 132, but the moment I fit and transform and convert, assign that to the same data set, you should see that my values are 0.15, 0.027. If I go all the way down, you should see a value of 1 here, because that is the maximum value which is scaled to 1. That value corresponds to this data point up here. Okay, so far so good. All we are doing is pre-processing our data to get it ready for our LSTM, for our deep learning, or I should say neural network. Okay, so so far we did our data set, and now we have to split this data set. You see we have 144 data points. Let's split that into a training data set and testing data set. Again, I mentioned this in the last few tutorials. The way we split this data set for time series is not by randomly picking data points like we do for other purposes, but by dividing the data into the first half and the second half, or first 2/3 and second 2/3. Because this is time series, and the data that's previous and after to this current data, it does have some meaning to it. That's why you have to chunk it that way. Okay, so here I'm going to take 70% of my data for training size. We can change that to 66% because that keeps it consistent to our previous tutorials. 66%, which is 2/3 as training, and the remaining as testing, and I'm assigning training and testing. So once this is done, you should see that my train size is 95 and test size is 49, and that's reflected in these dimensions of respective data sets. Okay, now again, all of this explanation for you guys. So because I'm sharing this file with you, go ahead and look at the link under the description here. And that's why don't take notes while watching this video. Just please stay focused in getting the message. You can always play with the code when you get your hands on it. Okay, now the data right now, if you look at my training data, it starts with 0.015 and 0.027 and so on. It's actually going down right here, but how do we train? What is our input and output to our neural network? What is the input and output to our LSTM? Well, the input is this. And when I say output, what is our X and Y? So we are trying to fit a model. A model means you have like a bunch of input values. You train a model to a predicted value output. Again, I did this discussion as part of our neural networks. Okay, so I'm not extending this discussion any further. I have written these, again, lines of code right there. All it's doing is it rearranges the input into X and Y format. We'll see that in a second. Okay, so let's run this. This is basically a function that reshapes my input data into a data of size, whatever. When I say sequence size equals to 5, my X will have like 5 of these and Y will be an output. So we'll see that in a second. Okay, so let's run these and run these two lines. And now let's compare. Okay, so test X, this is our test. The original, let's work with train. This is our train, the original training data points. This is our train X. These are the X values that's going into my neural network, LSTMs, for example. And train Y is the prediction. Okay, so we are fitting these values to this output and creating a model and using that model to predict future values. This is the story. Now, what do these numbers actually mean? If you look at this, this is nothing but the Y value is right here. And these are all the previous time steps. If you look at 0.059, it's right here, 0.059. Okay, keep an eye on that value, 0.059, 0.059. And all the other values here are the previous ones, 0.3281, 0.32, 0.04, 0.04, 0.54, 0.54, right there. And the next value here starts with 0.027 right there, and my y value is 0.84. So I do this incrementally because I'm looking back 5 steps in history. You can do 7 steps, and the farther you look, probably the better the model is going to predict. You can do that exercise yourself, okay? But you cannot just look very far in back, then you'll run into some issues again. You'll see that. But 5 days is fine, or 5 months in this case. 10 is probably fine, but if you do more than 40 or something, then you'll see some issues. But anyway, let's go ahead and do this. So hopefully you understand what our train X and train Y are doing now, right? I mean, what this function is doing. So now that we have our X and Y, we are all set to go ahead and train a model, but do we have data in the right format? So let's look at that. First of all, the model that we're going to use is somewhat like this, okay? So what does the model look like, okay? First, we are using sequential method, and then to that we are adding an LSTM with 64, okay, units. So 64 LSTM units, and my input shape is the sequence size shape. So I need to get my input to be in this shape. The input to this neural network, to this model, is first is the number of samples, and then the time steps, and then the features. That's exactly what I'm trying to do. I'm reshaping my train X right there into a shape of train X0, which is what? 89 by 1 time step by 5. Okay, again, go through this code at your own pace and understand that I'm doing exactly the same for testing. Okay, you have to do pretty much the same operation. So that's what this is. And if you look at my test train X and train Y, it's just reshaping the original data into this array format. That's pretty much it. The data itself is not changing. So instead of 89.5, it became 89.1 and 5 because the input to this model expects it that way. Okay, so this is the model. I'm just using single LSTM with 64 units, and then a dense layer of 32 and neurons, and then 1 neuron output, which is our Y value. Okay, now why am I using this? Absolutely, I have no clue why I'm using this. I want to put an LSTM, and I usually try 32, 64, started with 64, dense layers. I'm adding this dense. Is this the right architecture for this type of problem? We'll find that out. That's a completely different discussion where how you would like to do this architecture. Again, one thing I can tell you is do not put too many hidden layers, because then this will be overfitting on your training data, and it will not work very well on future forecasting. It works great on training. Okay, so it's a delicate balance. That's an art, and that's something you'll learn as experience. And please watch my video on how many hidden layers do you need. That will explain a little bit on this topic. Okay, so let's go ahead and print the summary. Okay, so the model summary is we have an LSTM layer and a hidden dense layer and an output layer right there with these many parameters. Now we are training 20,033 parameters in here. So now, again, we'll get to this other commented part in a minute, but let's go ahead and model.fit. This is how easy. We are done with LSTM part. All we had to do was just define LSTM right there, and you're done. Okay. And the rest of this is very similar to what we have done in the last few tutorials, which is go ahead and make predictions. The way you do that is model.predict, and predict on what? On my training data, model.predict on my testing data. And then the output that you get, train predict, is this. Well, this doesn't mean anything because all of this is the scaled value. Remember, we scaled everything. We scaled everything to, if I can go back here, min-max scalar, we have to undo that. Okay, so instead of scalar fit transform, we just do inverse transform down here once we are done. Okay, so let's go ahead and do inverse transform for both training and testing. And now if you look at test train Y, test Y right there. So these are the output values: 355,000 passengers, 422,000 passengers. So this actually means something right now, but we don't know how good it is or how bad it is. So let's go ahead and compare it and report a mean squared error. So all I'm trying to do is use square root and of the mean squared error value, which is between my train y and train predict. Okay, the train y is the amount, the training data that we have, and the train predict is the prediction that we just made. Okay, and y is 0 because we are just looking at the first column. That's it. Okay, let's go ahead and print the training and the testing scores, and looks like 22 RMSE, 47 RMSE. Is it good or bad? Compare this with other models and see how that works out for you. Okay, and in fact, let's do that. Let's change this model. Let's add 2 LSTMs and see how that actually gets better or worse. Okay, now I'm going to go ahead and plot all of these. Again, look at the code yourself, but there you go. I think I made a mistake here in terms of shifting the values by 1, because you see how everything is shifted a little bit. So I again apologize. If you find a mistake, let me know in the comments part so I can fix it for others. Okay, so all I'm trying to do here is just shift everything by 1. Maybe I should shift everything by 1 back. Yeah, so they kind of match. Anyway, so let's actually comment this part out. Okay, and let's undo. Where do we do that? Okay, let's undo from here. So here, this is 2 LSTMs now. And the way you stack 2 LSTMs is, please remember to add this line. Return sequences equal to true, otherwise it doesn't return the sequence, so there is no input to your next LSTM. So this LSTM expects this type of output from the previous layer. So go ahead and add that line, and now all I did is I took the previous model and just added another LSTM. That's pretty much it. Okay, I don't even think I need to reshape this because I already reshaped it in the right way. So let's go ahead and run all of these one more time. To have a shape, probably. Okay, let's remove all the variables because I'm reshaping an already reshaped data frame. So let's go ahead and not do that. Run the entire code, and hopefully we should see. Yeah, again, I think it's shifted by the wrong amount, but let's just look at the training: 22.85, 53.32. This is almost identical to single LSTM where we had 22-ish and then 47 or something for testing. Okay, again, I'll let you experiment with all of this. I have all the code here, so go ahead and just download, use it. Now, one thing I would like to show is how to implement this bidirectional. So let me just go ahead and uncomment all of this. The bidirectional is sorry, I shouldn't uncomment that part and this part. Okay. Like I said, in some sequences, there may be meaning in the forward direction and in the backward direction. So you can use bidirectional right there. And again, just like LSTM, it's very simple. Before LSTM, you just put this bidirectional right there. Of course, you have to import it from keras.layers. That is pretty much it. Everything else is exactly the same. So let's see how the model actually performs with this. I think the model shape, input shape should exactly be the same because we are still using LSTM right there. I think only for convolutional we'll have to change that. Let's see once we get there. Let's run this entire thing one more time. And this also should be pretty fast actually. Okay. So again, just because it doesn't work out great, you see right now the mean squared error actually went up from 22 and 50 to 29 and 71, and there is more going on right there. So again, maybe there is no lag, it's just that the way it's forecasting. But anyway, just because the bidirectional didn't work right here doesn't mean it's a bad model. This data doesn't mean anything when it comes to forward and backward directions, but again, you may have some data, maybe text classification, I don't know, but depending on the problem, use the right approach. Most of the time for time series, standard LSTM is pretty good. Okay, so don't experiment with different layers, but I don't think you need to worry about this bidirectional. Finally, let's finish this off with our training. I'm not reshaping it anywhere else. Okay, so that's good. So let's finish it off with our convolutional LSTM, and as the name suggests, it's basically a convolution 2D operation plus LSTM right there, all within one cell. That's what convolution means. Okay, again, of course, here I'm defining the kernel size right there. And after that, I'm just flattening it, because convolution 2D means you have 2D information. And for dense layers, you need 1D vector. So I'm flattening it, and then I'm providing dense, hidden layer, and dense. Now, again, when do we use this? I should admit my ignorance on this topic. I've never ever used convolutional LSM. I just experimented just like this, but I never found the need or experimented with this on real life use cases. But let's go ahead and run this, okay, to see how it's actually performing. Again, like I said, my goal here is to make sure you know these things exist and how to use them, so you can go ahead and explore these topics further. So here again, the training score is 24 and 54, not that bad. Okay, so apparently the bidirectional one was bad for whatever reason, and everything else seems to be slightly better. Now, one other experiment you can actually do is, okay, change the sequence size from 5 to 10. Does it actually improve or hurt? Okay, let's go ahead and again remove all the variables, and this, I promise, is the last experiment I'm going to do, but I'll let you go ahead and play with this after this. So let's see how this affects. I know for regular neural networks that has a big effect. Okay, it's slightly improved on the training, and on the testing it did not improve by a lot, but I said I promised that was the last thing. But let's actually look at the dense layer. This is the tutorial I've done 2 tutorials ago, and just to show you the effect of the depth, I believe this is where it works, but we'll find out. So my sequence size is 5 here, and I'm getting much better values, 16 and 36 for RMSE. And now let me change this to 10, and let's do this one more time. Okay. And now I got 14 and 29, so it's slightly improved, not by a lot, but it's slightly improved. And you see it matches very well. So maybe I was thinking fine when it comes to plotting here. Maybe the issue was it was actually predicting it in a wrong way, and we had like higher RMSEs. That's why it's not matching very well. So experiment with various parameters on LSTM. Add a layer, add dense layer, and maybe remove a dense layer. Only use single LSTM. That probably works better than adding a dense layer, especially for the forecasting part. Okay, so anyway, there's so much you can do with this, and I don't want this video to be any longer. It's already 20+ minutes, I believe, and we can explore this and make this a 1-hour video, but I'm pretty sure half of you are probably left by now. And for the remaining ones, thanks for your patience, and please do subscribe to my channel. Keeps me encouraged to create more such content. Thank you very much. And in the next tutorial, let's try to implement LSTM for text classification. Maybe we can start training the machine to write its own words and maybe its own documents. So we'll see what comes next. So thank you very much.